So last but before class we were doing in fourth module, additional to understanding a first moment of surface area, second moment of area, or otherwise called area moment of inertia. We were trying to understand what would happen if the section orientation is changed for the area moment of inertia with reference to a new rotated axis set. So that's where we have understood there is another term called the product of inertia that is going to influence your area moment of inertia, right? And of course, through that we were able to define what do you mean by principal axis and principal moment of inertia. So any arbitrary section can have maximum and minimum values of area moment of inertia, and you would have at that time zero product of inertia about the axis set, and those axis sets are called principal axis of the section. This principal axis can also be a centroidal principal axis, but it is not necessary all the centroidal axis should act as a principal axis, right? For this, you can understand the two sections. One is a rectangular section you take, or circular section you take. You have centroidal axis which are symmetry axis. So those axes are principal axis are called centroidal principal axis. But you can also look at a right angle triangle. So you have their centroidal axis which are not symmetry axis and they are not principal axis also. So you have to understand the statement. Principal axis can act as a centroidal axis, but all the centroidal axis of the section not necessarily to be a principal axis. So what do I mean by that? Whenever the centroidal axis or the principal axis, about that axis set, product of inertia is zero. Whenever, but all centroidal axes are not principal axis. That means you can have a centroidal axis wherein you also have product of inertia about that axis set. The best example is right angle triangle section, right? So with that note, we will enter to what we were doing in the last class to see and then continue from there. So after this understanding of principal axis and principal moment of inertia, product of inertia, we have mass moment of inertia. So we will have to relate this section property to a rigid body property, and that completes module 4. And then we will have 2 lectures for virtual work method, and we would be able to enter into comfortably on rigid body dynamics. So this is what our plan for future lecture. And let me share my ActinSphere board. Hope you are able to see this board. So this was lecture number 32, just before your CAT 2 examination we had. So that day we had understood what is, how do you define product of inertia mathematically, and also you can prove that product of inertia also can have an application of transfer theorem. So that's very much evident from this slide picture. You can see there is an arbitrary area. It has got its centroidal axis set, xg, yg axis, and the entire section and this axis set is defined by ox, oy axis. So we were able to prove parallel axis theorem holds good for product of inertia as well. And then we continued with that, looking at a simple section, standard sections, rectangular section, and we were able to derive what is Ixy. So if you are interested in particular quantity product of inertia, first get that for for the elemental area. If you know for the elemental area product of inertia, you would be able to get it for an entire area. That is the idea. So we would also use that similar concept in deriving expression for mass moment of inertia of the rigid body when they are undergoing rotation, right? See that you could apply this mathematical expression integral xy dA, and you are able to get your expression for rectangular area. Similarly, you can do so for right angle triangle and so on. And for all standard geometry, you can derive that. That's what we were seeing. So I was telling you this just some time back. When you have centroidal axis, which are symmetry axis of the section, we have here 3 sections: rectangle, circle, and triangular section. So rectangle and circle section, these centroidal axes are also called the principal axis, because about that axis set, you have product of inertia 0, right? But the same is not true if I represent even the rectangle, but the axes are not symmetry axes. Axes are XY axis, like here it is shown, like in this show it is shown, right? So I take this corner, I take this, and just a minute, some issue with my pen. Right? There's some problem with my stylus. Let me find out why. Okay, so let's understand this. Let me get by the time it's working. See here in this rectangular section, with respect to XY axis set for a rectangle, which is not the central axis, I can have my product of inertia. So then you look at the area, is it placed in first quadrant, second quadrant, third quadrant, fourth quadrant? Why? Because product of inertia can be negative, can be 0, or can be positive. Unlike area moment of inertia is always positive, product of inertia can have positive value or negative value or 0 value. And this is what you have understood, right, from this slide. And then we were in looking at what would happen in case I represent my section other than XY axis set with X dash, Y dash axis set. That's where you have an influence of product of inertia. So we were just doing this derivation, generic section we consider, and we did this derivation in the last class. Having a elemental area represented with respect to OX dash, OY dash axis set. So we get a new coordinate for the elemental area, X dash, Y dash, and that we have used to derive the expression of Ix dash. So you see in Ix dash, you have Ix, Iy for the any standard section about XY axis set, and X dash axis is represented with respect to X axis by an angular rotation of theta in your configuration diagram. So that theta and product of inertia is going to influence now the value of your area moment of inertia. That's what you understand from equation 1. And similarly, from equation 2, you would understand even the area moment of inertia with respect to y dash axis also influenced by the orientation of the new axis set from the previous axis set, the angle theta, and your product of inertia. And we have also carefully understood if I apply perpendicular axis theorem for Ix dash, Iy dash, I add them, what is happening is you have that's equal to Ix, Iy. That means we are changing the orientation of the plane, but that does not change the polar moment of inertia. So that is very important observation here. And we continued with that to represent simplicity of finding out this axis orientation. As I change my axis orientation of this rectangle by an angle theta, I can have what would be the angle theta it should be rotated, so that the new axis set also would have my product of inertia 0, and those axis set become principal axis set. So that is what I am interested in finding out. So if that is so, I can do that by eliminating this angle theta from this equation, 3 equations. So what we were doing is to eliminate that, we have taken equation 1 and 2, and we group them as a trigonometric term on one side and non-trigonometric term on the other side, and then we squared and added, and we have looked at added with what? Added with equation. So for example, you take equation 3, square them and add with equation 4. So you are adding Ix dash plus Ix dash Y dash, their respective squares, right? Add so that's what you are doing. So you are adding equation 3 and 4 here. So equation 3 is this, equation 4 is this. You are just adding squaring them and then adding. So equation 4 also you see there is a non-trigonometric term, that's an average value of your second moment of area that you have taken to the left side and you are squaring it. And similarly equation 3 you have squared and you are adding it, and automatically this theta get cancelled out because you have during the addition sine squared 2 theta plus cos squared 2 theta, which becomes 1, and that disappears, that's eliminated. And then you see that this equation representing the parametric equation of a circle, and that is where we have represented the entire formula sets that ix dash iy dash ix dash y dash all in a graphical method called Mohr circle, by means of Mohr circle. So that's where we just have stopped our previous class. Let's continue with that now to solve a single problem to confirm this procedure, right? So you can solve this. What will be asked in the exam is you will be given a section and you would be asked to find out its maximum and minimum moment of inertia values either by using formulas or by using a graphical method. So the method may be up to your choice to solve. Let's solve a single problem to adhere to this, right? So